Hello friends, this is Josh, and today we're going over Homework 3, Mass Balance. So, our homework problem is as follows. We have a flow Q1 entering tank 1, shown here. And from there, there's going to be another flow Q2 going between tank 1 and tank 2. Then we're going to have a final flow exiting the second tank, labeled as Q2. So, first thing we're going to do is we're going to put down all of our given information. So, we know that the cross-sectional area, the area of this tank, cross-sectional area of this tank, is going to be 1 meter squared. So, A1 is 1 meter squared. We know the cross-sectional area of tank 2 is 1.5 meters squared. So area of tank 2 is here. We have a flow Q1 entering tank 1 through here. Then we're going to have some flow Q12 going from tank 1 to tank 2. Then we have another flow Q2 exiting. So, we know that Q12, as given in the problem, is going to be equal 0.5 times the square root of H1 minus H2. And then Q2, as given by the problem, is going to be equal to 0.25 times the square root of H2. All right, and H1 and H2 are going to be our initial heights. So H1 is going to be the height of this liquid here, and H2 is going to be the height of this liquid. So the problem gives us initial values for H1 and H2. So at time 0, H1 at time 0 is going to be equal to 2.0 meters, and H2, the initial height of the second one, is going to be equal to 1.5 meters. So, and of course, as time goes on, H1 and H2 are going to vary according to our flows. So this is all of our given information. Now, to solve this problem, what we're going to do is we're going to solve a mass balance. So, in our case, we're going to use the basic mass balance equation. So that equation states what we input into our system being the two tanks, plus what's generated within the system, minus what we take out, the output, minus what's consumed by the system, is going to equal is going to equal the accumulation of the system. So, in our case, since we have no reactions at all going on, we will have no consumed and no generated quantities. So in this system, we have an input Q1, an output Q2, and our accumulation is going to be shown by changing heights of H1 and H2. So we use this equation whenever we have any sort of mass balance going on over a set period of time. So Q1, Q12, and Q2 are all volumetric flows. So what that is our Q1 is going to be equal to some change in volume, change in time. So that's what this unit represents. So volume can be written as the cross-sectional area times the change in height over the change in time. So what we're going to do is we're going to set up our equations to show off, all right, the input into the system, the output out of the system, and how it accumulates. So looking first at tank 1, we have an input into tank 1, Q1, an output out of tank 1, Q12, and an accumulation shown by H1. So focusing on tank 1, our input is Q1 minus our output of Q12 is going to equal our area, tank 1, times the height of 1 over time. So from here, what we're going to do is we're going to divide the cross-sectional area of the tank, and we're left with H1 over T equals Q1 minus Q12 over A1. And since we're looking for the change, how H1 and how H1 changes with respect to T, we're going to rewrite this as dH dt equals Q1 minus Q12 over A1. So this is our first equation, and this models how the height of tank 1 changes with respect to time. Now, doing the same for tank 2. Tank 2 is here, and we have an input, Q12, we have an output, Q2, and we have our same cross-sectional area times height. So we're going to have a Q12 minus Q2 is our input minus our output. That's going to equal our accumulation of A2 times the change in H2 as time changes. So dividing the same way we did before, we get change in H2 over the change in time, and that equals Q12 minus Q2 over A2. So this equation here and this equation here are what we're going to use to solve for how these heights change over the time. And we're going to do this over the interval of 100 seconds. So that should give us a good picture of what's going on with the system. And so what we're going to do is we're going to take these equations, this one and this one, and we're going to put it into our Google Colaboratory program and solve for it when Q1, our initial flow here, equals 1 meter cubed per second, which then changes to 1.5 meters cubed per second when T is greater than or equal to 50 seconds. So our total time interval is going to go between 0 and 100 seconds. Hello everyone, this is Josh and welcome to part 2. So, in part 1 we derived two differential equations to determine the height of two tanks given a time. So, in part 2 of this video we are going to create a script that will show how the height of both tanks change over the course of 100 seconds. So, the first thing we're going to do is we're going to import all the stuff we're going to need. So, first thing we're going to need is we're going to need a program to solve initial value problems. So, we're going to import solve IVP, and we're going to call that IVP to make it easier. And we're importing that from skippy.integrate, which is a Python program used for integration and other calculus related problems. So we're also going to import, excuse my spelling, we're also going to import numpy, and we're going to call that np. And then we're also going to import an interpolating problem for later. And we're also going to input a subplot program, which will allow us to make a subplot from all the data we're going to get. So we're going to import this from Plotly. And we're going to import the make subplots function. We're going to call that, we're just going to call that subplots. All right, and the final thing we're going to import is Plotly. All right. So these are all the things we're going to need to start the code. Okay, so what we're going to do now is we're going to create a function. We're going to call it DHDT. We're going to create a function that has both of our equations and can come up with height values as time changes. So, the two variables we're going to need are t and y. T is for time, obviously, and y is going to be our height values. So, what we're going to do is we're actually going to make our y, we're going to make our y into a table, or into, an array. So, the first values of the arrays the first value of the array is going to be the height of tank 1, and the second one is going to be the height of tank 2. Okay, and because Python starts its indexes at 0, the first term in this array is going to be at index 0, and that's going to be the height of tank 1, and the second term, index 1, is going to be the height of tank 2. So, then what we're going to do is we're going to put in our Q1 and our Q2 terms that we got as initial conditions with the problem. So our Q1, or our Q12 program, So initially we were given an equation of 0.5 times square root of height 1 minus height 2. So this was our equation for Q12. And our equation for Q2 is similar, except we're going to have 0.025 or 0.25 times square root of H2. So these are our given equations to find the flow rate between tank 1 and 2 and then out of tank 2. So the equations we derived in part 1, we're going to call those DH1 and DH2. So DH1 is going to be Qin as a function of t minus Q12 all divided by 1.0. And now our DH2, our second equation, is going to be Q12 minus Q2 divided by the area of the cross-sectional area of the second tank, which is 1.5 meters squared. So these are our equations. And what we're going to do is we're going to use this function to basically spit out values for each of these as time goes on. So whenever we run this function, we're going to want to return DH1 and DH2. Okay? So we're going to run that to check it for errors, and it looks like we got all the syntax right. So now what we're going to do is we're going to set up our initial value problem. So first thing we're going to do is we're going to pull the initial values of H1 and H2 from our problem. So H initial is going to equal 2 and 1.5. So 2 is the initial height of tank 1 and 1.5 is the initial height of tank 2. We also have Qn V. So this is going to be the flow rate going into the tank, Qn. And it's going to initially start at 1 meter cubed per second. And then it's going to change to 1.5 meters cubed per second. And it's going to end at 1.5. Okay? So, however, it's going to change when t equals 50. So what we have to do is we have to make a second variable, q and t, and specify when each of these values happen. So we're going to set this from 0 to 50 to 100. Because our thing is going from 0 to 100. And it changes to 1.5 at 50 seconds, which is why we have that number specifically here. So, knowing Q and V and Q and T, we can then create our Q in variable. And the way we do that is we use that interpolate function that we imported earlier. So inter P1D of Q in T, Q in V, so what this is going to do is it's going to match up these two values in order to, so that we can eventually put this on a scatter plot. And it's also going to be able to let us use these values in these equations up here. because what's going to let us do is it's going to let us use 1 as our QNV value, while time is between 0 and 50. And then when it hits 50, it's going to shift this QN value here to 1.5. And that's going to continue on until we hit the final value of 100, where it's going to stop. So what we're going to do is we're going to match up our values with the previous command. So, having all that now, what we're going to do is we're going to create our IVP. So our result equals IVP, which is our solve IVP program from before. Then we're going to import our DHDT function we created in step 2. And then we're going to specify our time, our inner and outer bounds for time. Then we're going to give it the initial values for tank 1 and tank 2. Then we're going to use the RADU method to solve this initial value problem. And we are going to set dense output set to true, because it's normally set to false, but we want it true in this case because we need all of the outputs as it iterates so we can plot them all. Okay, so now that we're here, we're going to run this to make sure there's no syntax errors. Cool. Now that we have all of our equations, time to plot them. So first thing we have to do is we have to create our variable for time. So the way we're going to do that is we're going to set t equals numpy dot line space 0, 100, 100. And that's going to give us every value between 0 and 100 as our time. Right? Yeah. So that'll allow us to iterate over the course of 100 seconds. So our solution is going to be take this equation we have here and iterate it over this time interval we created. So now that we have that, we're going to create our figure. So we're going to name our figure just fig to make it easy for us. So we're going to use subplots, which again we imported here from Plotly subplots. And we're going to set our kind of settings for our subplots with 1 row and 1 column. And then we're going to add our scatter. We're going to add our scatter plot for tank 1. What this will do is this will take our DH1 equation and basically iterate it over the interval we created here from 0 to 100 seconds, and it's going to plot that data on the figure we just created. So we're going to specify that our t is going to be our x variable. So what that means is our t time is going to run along the horizontal axis. Our y value along the vertical axis is going to be this answer here, which is our iterative thing, and it's going to be the first index. Because remember, this will create an array with two indexes, and the second index is going to be for this equation here, which will give us for tank 2. So we'll use that in a second. But anyway, so we're going to name this, tank 1. And then we're going to do the exact same thing for the second tank. So x is going to be equal to time y equal to the solution of index 1, and we're going to name it tank 2. And now that we have this is basically all we need for our scatter plots to get the actual data on there. So what we're going to do now is we're just going to make our scatter plot a little bit easier for us to read. So we're going to update the layout, and we're going to dictate that the width is going to equal 500. And the height of the plot is going to equal 400. What that'll do is it'll give us a nice rectangular 5x4 plot. And then we're also going to add in our legend orientation. Set that equal to h value. And that'll give us our legend at the bottom of the graph in one line. So, and we're actually going to specify that. So, legend x equals 0.5. And we're going to center the legend along the bottom of our scatter plot. Excuse me. And now we're going to specify its y direction. We're going to set that equal to, say, -0.2. -0.2. And that's just going to put our legend where we want it. And it's going to be away from our data and kind of below the actual graph. So our x-axis title we're going to name time in seconds. Our y-axis title is going to equal height in meters, because remember our y-axis is the height of our two tanks. And then we're reaching the end of the screen, so we're going to enter over, but remember all this is one line. So we want to show our y-axis grid to make it a little easier to read. So y-axis underscore show grid. We're going to set that to true. And we're going to set our So keep in mind our x-axis goes from 0 to 100. So we're going to want it to tick every 10 seconds. So the way we do that is we do every x-axis dtick and set that equal to 10. And now finally, we're going to title our scatter plot. So we're going to set our title as just a 2-tank simulation. Make it nice, short and sweet. And then we're just going to put that title in the center. So, I know that was a lot of code. What that'll do is that'll make our graph look nice. So, what we're going to do is we're going to show our figure. So, running all this, we get this nice graph. So as you can see, as time goes on, the height in both tanks, it starts out increasing quickly, but as time goes on, both tanks start to kind of flatten out. However, as soon as they hit 50, you see another spike because the flow into the tanks increases to 1.5 meters cubed per second. So both tanks take a steeper slope and jump up higher. So if the time was increased past 100, we would eventually see a point where the graphs would flatten out and stay constant. However, since we are only looking at the time interval from 0 to 100, they're both increasing. So this is the answer. This is 2 tanks in series. And this is what our graphs are going to look like. So, thank you all for watching, and I will see you later.